Welcome to the deep dive. Our mission today is, well, it's absolute mastery. We're not just aiming to understand, but really own the detailed, high-stakes architecture of our two most critical sensory systems.
That's right.
We are going deep, really deep into the histology and function of the eye and the ear.
And these are arguably just the most complex mechanical and biochemical portals in the entire human body. I mean, the source material we're drawing from, it's dense, it's clinical.
It is.
It really demands a professional level of understanding. We're definitely going beyond the standard textbook basics today.
Much beyond. We're planning to dissect the precise cellular, the tissue organization, everything that actually enables sight, hearing, and equilibrium.
Exactly.
So this isn't going to be a quick summary. We're essentially mapping the entire internal geometry. We'll be covering, well, everything from the three tunics of the eye, the kind of counterintuitive physics of phototransduction, all the way to the dual labyrinth system in the ear, and that high potassium battery, the one that drives mechanotransduction.
And it's really vital I had to frame this correctly from the start. These organs, they are just standalone receivers. Not at all.
No.
They are highly specialized extensions of the central nervous system, the CNS. And they rely on these structurally unique components. Think about it, vascular tissues, highly ordered connective tissue, specific ionic fluids.
Things you don't see everywhere else.
Precisely. So mastery here really means grasping the structural trade-offs, the architectural precision required for all these diverse components to work together flawlessly, in concert.
Okay then, let's unpack this. It feels like a monumental task, but let's start with the eye, our photoreceptor system. Fundamentally, the eye serves a protective purpose, obviously, but its main job is optical, right? Precise refraction and focusing of light.
Exactly. And the eyeball itself, structurally, is defined by three concentric layers. Tunics, we call them.
Tunics.
The outermost is the fibrous layer. Think tough, structural protection. This layer includes the posterior 5/6, which is the white, opaque part. You see the sclera. That's made of dense type ecology.
Right.
And the sclera is crucial because that's where all the extraocular muscles insert. It allows us to move our gaze.
Got it. And the front part of that fibrous layer, that's the clear window.
That's the cornea, the anterior 1/6. It's transparent, and it's actually the primary light-bending structure of the entire optical system.
Okay.
It does most of the heavy lifting for refraction.
Okay, so layer one, fibrous, sclera, and cornea. What's underneath that?
Beneath the fibrous layer lies the middle one, the vascular layer. It's universally known as the uvea.
The uvea, right. And that sounds like, well, the supply and regulation hub.
That's a good way to put it. It consists of the highly vascularized choroid, then the ciliary body, and the light-regulating aperture itself, the iris.
Okay, uvea, got it. Choroid, ciliary body, iris.
And then finally we arrive at the innermost layer, the inner sensory layer. That's the retina.
The business end.
That's the neural tissue itself. It communicates directly with the cerebrum via the optic nerve. It's where the actual event of light conversion, phototransduction, takes place.
And what's interesting here, you mentioned the layers, but there are crucial parts that aren't tunics, right? Things like the lens.
Absolutely essential. The lens, perfectly transparent, biconvex, and the huge gelatinous vitreous body that fills that big posterior chamber. They aren't layered tunics, but they're absolutely critical for focusing light and just maintaining the eye shape. #2.
Okay.
Deep dive into the fibrous tunic, sclera and cornea.
Okay, so to really achieve mastery, we have to spend some serious time on the cornea, don't we? You called it the primary light-bending structure.
We really do. It's an architectural marvel. It's completely avascular, no blood vessels, yet it's perfectly transparent and performs about 2/3 of the eye's total refractive power. It's incredible.
Okay, let's break it down. You mentioned 5 distinct layers. This level of detail feels, well, non-negotiable if we want to understand its function and things like surgery.
It really is.
Okay.
Let's go from the outside in. Layer 1,
Yeah.
the external corneal epithelium. It's stratified squamous epithelium, non-keratinized, about 5 to 6 layers thick, and it has a very high proliferative capacity. It regenerates constantly from stem cells located at the edge, the limbus.
And it must be super sensitive, right? It's right out there.
Extremely. You're one of those richly supplied tissues with sensory nerves in the whole body. Any touch, any irritant, instantly triggers that protective blinking reflex.
Makes perfect sense. It's the body's exposed window. Needs a hairdresser alarm. Okay, layer 1, epithelium. What's beneath that?
Beneath that is the anterior limiting membrane, also known as Bowman's membrane. Think of it as a very thick acellular basement membrane. It provides significant stability and acts as a powerful physical barrier against infection spreading deeper.
Okay, tough barrier. And then we get to the main bulk, the thickest part.
That's the stroma, or substantia propria. It makes up a massive 90% of the cornea's thickness, and its transparency is achieved through sheer architectural perfection. It consists of approximately 60 layers, or lamellae, of type I collagen bundles. These bundles are rigorously parallel within each layer, but crucially, they are precisely orthogonally arranged relative to the bundles in adjacent layers, like plywood almost.
Wow, okay. 90 degrees rotation between layers.
Exactly. And scattered throughout are specialized cells called keratocytes. They're basically flattened fibroblasts, which maintain this incredibly precise geometry and synthesize the matrix components.
So it sounds like absolute geometric precision is just essential. If the spacing between those collagen fibrils gets messed up even slightly, say by too much water,
Transparency is lost instantly. The spacing is maintained by specific proteoglycans like lumican, and if hydration changes even a little bit, light scatter increases dramatically. The cornea basically prioritizes this architectural perfection over having a traditional blood supply.
incredible trade-off. Okay, stroma is layer 3. What's next?
Next, layer 4, we have the posterior limiting membrane, also called Descemet's membrane, another strong basement membrane, secreted by the layer underneath it.
And that final critical internal layer, number 5.
The inner simple squamous endothelium. Now, this looks like just a simple single layer of cells lining the back, but our sources emphasize it as the most metabolically active layer of the whole cornea
Really? Why so active for just a simple lining?
because it controls the cornea's hydration and therefore its integrity. The cells of this endothelium are packed with highly active NAN plus K plus ATPase pumps, mostly on their basolateral membranes.
Okay, ion pumps.
These pumps actively transport ions out of the stroma, and water follows osmotically. They're constantly pumping water out of the stroma to prevent it from swelling. If this endothelial layer fails, the stroma swells, that precise collagen spacing is lost, and the cornea becomes opaque. It's the life support system for corneal clarity.
Okay, now the practical payoff. We've all heard of all-sex surgery. Understanding these layers makes it clear what's happening. When surgeons use that excimer laser, they're targeting layer 3, right, the stroma.
Exactly. ALSIC involves creating a thin flap, usually in the epithelium and Bowman's membrane, folding it back,
Exposing the stroma?
and then using the laser to precisely vaporize microscopic amounts of collagen and keratocytes within the stroma. This reshapes the curvature to correct refractive errors like myopia or hyperopia. The success hinges entirely on the predictable structure of the stroma and the epithelium's ability to heal over the reshaped area.
And the success of corneal grafts, they're often called immunologically privileged. That directly relates to this fibrous tunics design too, doesn't it?
It absolutely does. That immunological advantage comes directly from the cornea's complete lack of vascular supply. No blood vessels,
Right.
and just as importantly, no lymphatic drainage either. This combination minimizes the presentation of foreign antigens to the host's immune system. It promotes local immune tolerance, leading to a significantly lower rejection rate compared to, say, a kidney or heart transplant. #TechTechTree, aqueous humor dynamics, and the limbus.
All right, let's follow the internal plumbing now. We need to talk about the fluid inside the front of the eye and where it goes. This brings us to the limbus. That's the transitional zone, right? Where the clear cornea meets the white sclera.
Precisely. The limbus, or the corneoscleral junction. Structurally, it's significant because it's where Bowman's membrane ends. Functionally, it's critical because it houses those epithelial stem cells we mentioned, the ones responsible for constantly renewing the corneal epithelium.
But it's also key for fluid management, the dynamics of aqueous humor.
Paramount, yes.
Right.
Let's trace the flow, because if this system clogs up, the entire mechanical integrity of the eye is under threat.
Okay, where does the aqueous humor come from?
It's a clear, low-protein fluid. It's actively secreted by specialized, non-pigmented epithelial cells that cover the ciliary processes. We'll talk more about those shortly. These processes are part of the ciliary body.
Okay, secreted behind the iris.
Into the posterior chamber, yes.
Right.
The small space between the iris, the lens, and the ciliary body. From there, it flows forward through the pupil into the large anterior chamber, the space between the cornea and the iris. And the drainage system for this fluid is located right there at the edge, in the angle formed by the iris and the cornea, essentially, at the lingus.
So it bathes the lens and the iris, provides nutrients, and then it needs to get out. How does it exit?
First, it has to filter through a complex, sponge-like network of irregular endothelium-lined channels. This is known as the trabecular meshwork. It's located deep within the limbal stroma, right at that angle.
Like a biological filter.
Exactly. It acts as a selective filter.
Mm.
From the meshwork, the fluid then flows into a larger, specialized circular channel called the scleral venous sinus, or more classically, the canal of Schlemm.
Canal of Schlemm. Okay.
This canal rings the cornea within the sclera. And finally, from the canal of Schlemm, the aqueous humor drains into small scleral venules and rejoins the general venous circulation.
Wow. Okay, so the eye is basically running its own internal river system. And if the filter, that trabecular meshwork, gets clogged,
The whole system pressurizes.
and the medical implication is immediate and, frankly, terrifying: glaucoma.
Glaucoma is precisely the consequence of impeded drainage. Usually, it's due to increased resistance or obstruction within the trabecular meshwork, or maybe the venous sinus downstream. This blockage causes the intraocular pressure, IOP, to rise.
And it's the pressure itself that's the danger, not the fluid.
Correct. The source of the threat isn't the fluid, it's the resulting mechanical pressure.
And where does that pressure cause the damage? What's the risk?
The severe risk is that this increased IOP pushes the large, gelatinous vitreous body backward. And the vitreous body then presses against the delicate neural structure of the retina, specifically damaging the ganglion cells and the optic nerve head where the axons exit the eye.
Leading to vision loss.
Progressive, irreversible visual field loss, optic neuropathy. We should also quickly distinguish acute angle closure glaucoma. That's a bit different.
How so?
In some individuals, the angle between the iris and cornea is naturally narrow. If the pupil dilates significantly, the peripheral iris can bunch up and physically block access to the trabecular meshwork, completely shutting off drainage.
Like slamming a door shut.
Exactly. This causes a rapid, painful spike in IOP. It's a true ophthalmic emergency, requiring immediate surgical intervention, often creating a small hole in the iris, an iridotomy to relieve the pressure before permanent damage occurs.
Okay, moving deeper into the eye now, let's explore that middle layer, the uvea, the vascular tunic. You said it provides nourishment and controls light intensity.
That's right. Posteriorly, covering most of the back of the eye, sandwiched between the sclera and the retina, we find the choroid.
Okay.
This is a layer of loose connective tissue, but it's heavily invested with blood vessels, extremely vascular. And importantly, it's rich in melanocytes, pigment cells.
Why the pigment here?
The sheer density of melanocytes creates a dark, almost black layer. This dark layer absorbs any extraneous light that might pass through the retina or scatter sideways. It prevents internal reflections, which would blur the image, like the black paint inside a camera.
Ah, okay. And the choroid itself? Does it have different parts or layers serving the retina?
It does have a functionally distinct inner layer. It's called the choroidocapillary lamina. This is a very rich network of capillaries, a dense microvasculature specifically tasked with providing metabolic support, oxygen, and nutrients to the outer layers of the retina, including the photoreceptors.
And that's separated from the retina by
a thin, cellular extracellular sheet known as Bruch's membrane. It acts as a basement membrane complex between the choroidocapillaris and the retina's own pigmented layer.
Okay, choroid is the posterior part. Now, moving forward, we hit the powerhouse, the ciliary body. It kind of encircles the lens, right? This structure seems like a marvel of specialization. It handles both mechanical action and secretion.
It really is multifunctional. The ciliary body contains the ciliary muscle. This is actually composed of 3 distinct groups of smooth muscle fibers. Their coordinated contraction is the critical biomechanical trigger for changing focus visual accommodation.
We'll definitely come back to accommodation.
Right.
What else is in the ciliary body?
Well, structurally, it projects inwards towards the lens as a series of radial ridges. These are the ciliary processes. And these processes are covered by a unique dual layer of epithelium. There's a pigmented epithelial layer deeper down, continuous with the retina's pigment layer, and then a non-pigmented surface epithelial layer facing the posterior chamber.
And those non-pigmented cells, they're the aqueous humor factories we mentioned earlier.
Those are the ones. They are highly specialized for active transport and secretion. They filter components from the capillaries in the ciliary body stroma and modify them to produce the aqueous humor. And as we noted, the key feature is its ionic composition, similar to plasma, but critically, it has almost zero protein content. This maintains the perfect optical clarity needed for light to pass through the chambers.
Okay. Ciliary body handles muscle action and fluid production. Now we arrive right at the front of the uvea, the iris, the structure that dictates our eye color and controls the pupil size. What's unique about its surface architecture, you mentioned something earlier.
The iris is the most anterior extension of the uvea, and its anterior surface is highly unusual. It actually lacks an epithelial covering.
No epithelium, really?
None. It consists only of a loose stroma containing fibroblasts and melanocytes, exposed directly to the aqueous humor in the anterior chamber. The posterior surface, however, is very different. It's heavily fortified by 2 layers of densely pigmented epithelium, continuous with the ciliary body epithelium. This ensures maximum light blocking, except for the light passing through the central aperture, the pupil.
And controlling that aperture, the pupil size, requires muscles working against each other, right? Like a camera diaphragm.
Exactly. There are 2 muscles within the iris stroma. The sphincter pupillae consists of smooth muscle fibers arranged circularly, very close to the pupil margin. It receives parasympathetic innervation via the oculomotor nerve. When it contracts, it constricts the pupil that's called meiosis.
Okay, parasympathetic constricts. What opens it?
The dilator pupillae. This muscle is arranged radially, like spokes on a wheel. Interestingly, it's composed of myoepithelial cells that have contractile processes. It receives sympathetic innervation. When it contracts, it pulls the pupil open, enlarging it. That's mydriasis.
Sympathetic dilates. Got it. And eye color. That's just down to the pigment cells in the stroma, the melanocytes.
It's purely a function of the density and distribution of those stromal melanocytes on the anterior surface, interacting with light. Low melanin content doesn't mean blue pigment. It means light scatters within the stroma, rayleigh scattering like the sky. And the only pigment you really see is the dark posterior epithelium reflected back through that scattering stromal haze. So, low pigment looks blue.
Ah, interesting.
Higher pigment density absorbs more light, leading to green, hazel, gray, or brown eyes. And if pigment is completely absent, as in oculocutaneous albinism,
Then it looks pink.
yes, because you're seeing the reflection of light off the blood vessels within the iris stroma itself. There's no melanin to mask it. Hashtag #tag55. The lens and accommodation mechanism.
Okay, now for the final refractive structure before we hit the retina itself, the lens. You defined it earlier by its transparency, its vascular nature, and its elasticity.
That's right. And that a vascular nature, again, means it has an incredible reliance on the aqueous humor in front and the vitreous humor behind for all its metabolic needs, nutrients in, waste out.
So what's it actually made of? What are its components?
It has 3 main parts. First, surrounding the whole thing is the lens capsule. This isn't a cellular capsule. It's a thick, transparent external lamina, like a very thick basement membrane composed mainly of type 5e collagen and proteoglycans. It's elastic, and crucially, it serves as the attachment site for the suspensory ligaments, the ciliary zonule.
Okay, capsule on the outside.
Just underneath the capsule, but only on the anterior side, is the subcapsular lens epithelium. This is a single layer of cuboidal epithelial cells. These cells are metabolically active and are the source for the cells that make up the bulk of the lens.
Which are the lens fibers, the core material.
Exactly. These are incredibly highly specialized cells. They actually develop from those epithelial cells near the lens equator. They become intensely elongated, stretching from the front to the back of the lens. And as they mature, they fill their cytoplasm almost entirely with structural proteins called crystallins.
Crystallins, okay.
These crystallins are arranged in a way that minimizes light scatter. And crucially, to achieve near-perfect transparency, these lens fiber cells undergo a remarkable process of selective autophagy. During differentiation, they completely lose their nuclei and all other membrane-bound organelles.
Wow. They basically self-destruct their insides for clarity.
Precisely. This dense packing of crystallins and the lack of internal organelles is what makes the lens transparent.
Okay, now let's connect this to visual accommodation, the mechanism for focusing on near and far objects. You mentioned it involves the ciliary muscle, the lens elasticity, and these suspensory ligaments, the ciliary zonule. How does that work?
The default setting for the eye is focus at a distance, say beyond 20 feet. In this resting state, the ciliary muscles are relaxed.
Relaxed for far vision.
When the ciliary muscle is relaxed, the diameter of the ring it forms is larger. This pulls the fibers of the ciliary zonule TUT. These taut zonule fibers, which attach to the lens capsule all around its equator, pull on the lens, flattening it.
So relaxed muscle, tight ligaments equals flat lens for distance.
Correct. Now, for near vision, when you need to focus on something close, the ciliary muscles contract. They receive parasympathetic signals to do this. This contraction makes the muscle ring smaller in diameter, moving the whole ciliary body slightly forward and inward toward the lens axis.
Okay, muscle contracts. What does that do to the zonule?
This contraction relieves the tension on the zonule fibers. They become slack.
Ah, so the muscle contraction doesn't squeeze the lens directly. It just gives the ligaments slack.
Exactly. That's the key insight. The muscle contraction provides slack in the system. And because the lens itself is inherently elastic, especially when we're younger,
It springs back.
it naturally springs back into its preferred, more rounded, and thicker shape. This more convex, rounded shape increases the lens's refractive power, allowing the eye to focus the light from nearby objects onto the retina.
That's a beautifully elegant mechanism. Muscle contracts, ligaments slacken, lens rounds up.
It really is.
And the failure of this elasticity, which happens to almost everyone as they age, that's presbyopia.
That's the structural failure of aging, pure and simple. Typically starting around age 40 or 45, the lens progressively loses its elasticity. The crystallines become less flexible, the capsule might stiffen. It just can't round up adequately anymore when the ciliary muscle contracts.
So near focus becomes difficult.
Exactly. Requiring reading glasses, which are convex lenses, to add the extra refractive power the natural lens can no longer provide. A more severe, though related issue is the cataract.
Where the lens itself becomes cloudy.
Yes. This involves the denaturation or aggregation of those crystalline proteins. The lens loses its transparency, becomes opaque or cloudy, and vision is significantly impaired. Could be due to age, UV exposure, diabetes, trauma. Many causes.
In modern cataract surgery, the surgeon doesn't just yank the whole lens out, do they? They preserve part of the structure.
That's right. Modern phacoemulsification surgery is incredibly precise. The surgeon makes tiny incisions, opens the anterior lens capsule, and then uses ultrasound to break up or emulsify the opaque lens substance within the capsule. This is then aspirated out.
But they leave the capsule.
Crucially, they are meticulous about leaving the posterior side of the lens capsule and its attachment to the zonular fibers completely intact. This posterior capsule forms a natural, secure, concave capsular bag. And into this perfectly positioned bag, they implant an artificial, usually acrylic, intraocular lens, IOL prosthesis. This holds the new lens exactly where the old one was. It's a testament to microsurgical precision.
All right, finally. We've followed the light through the cornea, the pupil, the lens. Now we reach the destination, the retina, the inner sensory tunic. You mentioned it comes from the embryonic optic cup and has two distinct sublayers.
That's correct. The outer layer, lying against the choroid, is the single layer of cuboidal cells called the retinal pigmented epithelium, or RPE. The inner layer is the much thicker stratified neural retina. This is the nervous tissue proper.
And you highlighted a key structural risk here. These two layers, the RPE and the neural retina, aren't actually firmly joined by strong cellular attachments. Is that right?
That's a critical point. There's a potential space between them, derived from the cavity of the original optic vesicle.
Okay.
This means that trauma, or sometimes certain disease processes, can cause the neural retina to lift away from the RPE.
Which is retinal detachment.
Exactly. And it's a true medical emergency, because that separation cuts off the vital metabolic support, oxygen, nutrients, waste removal, provided by the underlying RPE and the choroid's capillaries, to the photoreceptor cells, the rods and cones.
So the photoreceptors start to die.
If the detachment isn't repaired quickly, surgically, the photoreceptor cells, which have incredibly high metabolic demands, begin to degenerate and die, leading to permanent vision loss in that area.
Okay, let's focus then on the absolutely essential functions of that outer layer, the RPE. You said it does far more than just absorb scattered light, supplementing the choroid.
It has at least 4 essential, really complex functions. First, yes, absorbing stray light is one. Second, its cells are joined by tight junctions, forming the crucial outer blood-retina barrier. This isolates the highly sensitive neural tissue from the fenestrated, leaky capillaries in the choroid.
Okay, barrier function, what else?
Third, it acts as a sanitation crew. It actively phagocytoses the shed outer segment tips, those membranous discs, from the adjacent photoreceptors. This is a massive continuous process, especially for rods.
Cleaning up the debris. And fourth, you called it the core of the visual recycling plant.
Right, the RPE is absolutely central to the visual cycle. Remember how light causes retinal vitamin A aldehyde to change shape in the photoreceptor? Well, after light converts the active form, 11-cis retinal, to the inactive all-trans retinal within the photoreceptor, that spent all-trans retinal is transported out of the photoreceptor and into the RPE cells. The RPE contains the specific enzymes needed to isomerize it back into the active 11-cis retinal form. This regenerated 11-cis retinal is then transported back to the photoreceptor, ready to detect another photon. The RPE constantly recycles the visual pigment.
Incredible. Okay, RPD is vital. Now for the neural retina itself, an actual outpost of the CNS, structured into 9 distinct layers of neurons and glia. That sounds complicated. How do we organize this? You mentioned nuclear layers and plexiform layers.
That's the standard way. We organize it by thinking about where the cell bodies are, nuclear layers, and where the synapses happen, plexiform layers. Starting from the outermost layer right next to the RPE, we have the photoreceptor layer itself, rods and cones, outer and inner segments. Then the outer nuclear layer, ONL. This contains the cell bodies, the nuclei, of the rods and cones.
Okay, ONL equals photoreceptor cell bodies.
Next layer inward is the outer plexiform layer, OPL. Plexiform means network or mesh. This is where the axons of the photoreceptors make synapses with the dendrites of the next set of neurons.
The first processing station.
Exactly. Those next neurons reside in the inner nuclear layer, INL. This layer is densely packed with the cell bodies of several types of crucial integrating neurons. The bipolar cells, the amacrine cells, and the horizontal cells. They start processing the visual signal.
Okay, INL, bipolar, amacrine, horizontal cell bodies, then another synaptic layer.
Yes, the inner plexiform layer, IPL. This is generally thicker and more complex than the OPL. Here, the axons of the bipolar cells and processes of amacrine cells synapse with the dendrites of the ganglion cells. Further processing happens here.
And finally, the output neurons?
The ganglionic layer, GL, or ganglion cell layer. This contains the cell bodies of the ganglion cells. These are the final output neurons of the retina. Their axons bundle together, run across the surface of the retina.
And form the optic nerve.
Correct. They converge at the optic disc and exit the eye as the optic nerve, carrying the processed visual information to the brain. There's also a nerve fiber layer, NFL, where these axons run.
Okay, that's 3 nuclear layers, ONL, INL, GL, and 2 plexiform layers, OPL, IPL, for synapses. But you mentioned 9 layers in total, and glia.
Right. We also need to account for the limiting membranes. And the primary glial cell here is unique, the Miller cell. These aren't just filler. They're large radial glial cells that span almost the entire thickness of the neural retina, from the outer edge to the inner edge.
What do they do?
They provide critical structural support, almost like pillars. They also provide metabolic support to the neurons, help regulate the extracellular environment, like buffering potassium ions and recycling neurotransmitters like glutamate, and contribute to the blood-retina barriers.
So they form the boundaries, too.
Yes. Their apical ends form adherens junctions with the photoreceptors, creating a boundary called the outer limiting layer, OLL, or external limiting membrane. And their expanded basal end feet spread out on the innermost surface of the retina, facing the vitreous body, forming the inner limiting membrane, ILM. So if you count the RPE, the photoreceptor layer, OLL, ONL, OPL, INL, IPL, GCL, NFL, and ILM, you get more than just the basic 5 neuron synapse layers. But the on-allopilin LPL GCL structure is the core processing pathway. #7, photoreceptors and phototransduction.
Okay, let's zoom in on the photoreceptors themselves now. Rods and cones. The structure dictates the function, you said.
Absolutely. Let's compare them. Rods, there are about 92 million of them in the human retina. They are responsible for scotopic vision, that's low-light nighttime vision. They are incredibly sensitive.
Capable of detecting a single photon, right?
Yes, under optimal conditions. Their outer segment, the light-catching part, is rod-shaped, obviously, and contains somewhere between 600 and 1,000 flattened, membrane-bound discs, stacked like coins. These discs are actually detached from the outer plasma membrane, except at the very base where they form.
And these discs are packed with
The visual pigment rhodopsin, often called visual purple. Now, what's fascinating is the metabolic churn here. These discs are constantly being assembled at the base of the outer segment, pushed distally, and then the oldest discs at the very tip are shed.
The RPE cleans them up.
Exactly. At a remarkable rate, about 90 discs per rod are shed and phagocytosed by the RPE every single day. It's a massive renewal process.
Wow. Okay, so rods equals high sensitivity, low light rhodopsin, high turnover. What about the cones? There are fewer of them.
Much fewer, only about 4.6 million. Cones are responsible for photopic vision in bright light and, crucially, for color vision and high visual acuity. They're less sensitive to light intensity than rods.
And their structure differs.
Yes. Their outer segment is typically shorter and conical. And instead of detached discs, their discs are formed by continuous invaginations or infoldings of the outer plasma membrane. They remain connected.
Ah, okay. Not separate discs.
Right, and they contain different visual pigments called iodopsins, or more accurately, photopsins. There are 3 classes of cones, each containing a photopsin maximally sensitive to different wavelengths of light, broadly corresponding to red, green, or blue light. This trichromacy is the basis of our color vision. Also, cone discs are shed much, much less frequently than rod discs.
Okay, different structure, different pigment, different function. Now let's trace the signal. The mechanism of phototransduction, say in a rod cell, starting in complete darkness. You mentioned this is crucial because it's entirely counterintuitive.
It really is. You have to flip your thinking. In
Oh.
darkness, the rod cell is actually quite active metabolically, and it's electrically depolarized.
Depolarized in the dark. That's weird.
It is. Here's why. In the dark, the rhodopsin pigment is inactive. It has 11 cis retinal bound. Inside the cell, the level of a signaling molecule called cyclic GMP, cGMP, is kept high by an enzyme called guanylate cyclase.
Okay, high cGMP in the dark.
This high concentration of cGMP directly binds to and keeps specific cation channels, permeable mainly to Na+ and some CT2+, on the outer segment plasma membrane open.
So ions flow in.
Sodium ions flow into the cell through these open channels, creating what's called the dark current. This influx of positive charge keeps the cell relatively depolarized, maybe around -40 millivolts.
And what does this depolarized state lead to?
It causes the continuous tonic release of neurotransmitters, specifically glutamate, from the rod cell synaptic terminal in the OPL onto the downstream bipolar neurons. So in the dark, the rod is constantly dumping glutamate. Resting state is on.
Okay, dark, depolarized, constantly releasing glutamate. Now, what happens when light finally hits the rhodopsin?
This is the cascade. A single photon is absorbed by the 11 cis retinal molecule within rhodopsin. This provides the energy for an instantaneous isomerization. The bent 11 cis shape flips to the straight all-trans retinal shape.
Shape change.
This shape change in retinal forces a conformational change in the protein part, opsin. This activated state of rhodopsin is sometimes called metarhodopsin tebin. This bleached rhodopsin now interacts with and activates a G protein called transducin. Hundreds of transducin molecules can be activated by one rhodopsin molecule.
So amplification starts right there.
Big time. Each activated transducin molecule then activates an enzyme called cGMP phosphodiesterase, PDE.
PDE breaks down cGMP.
Exactly. The activated PDE rapidly hydrolyzes cGMP, breaking it down to GMP. So the intracellular concentration of cGMP plummets very quickly.
Okay, cGMP level drops. What does that do to the channels?
Without sufficient cGMP to bind to them, those cation channels on the outer segment membrane close.
Ah, the dark current stops.
Yeah. The influx of Na+ stops. But potassium ions continue to leave the cell through leak channels in the inner segment. The net effect is that the inside of the cell becomes more negative. The cell hyperpolarizes, perhaps down to some 70 millivolts.
Hyperpolarizes in response to light.
Yes, and this hyperpolarization travels to the synaptic terminal and causes voltage-gated calcium channels there to close, reducing the influx of calcium. This finally leads to a reduced release of the neurotransmitter glutamate onto the bipolar cells.
So the fundamental signal for light detection is a decrease in glutamate release from the photoreceptor.
Precisely. Light causes the photoreceptor to shut down its baseline signaling. It's this reduction in glutamate that is then interpreted by different types of bipolar cells. Some are excited by less glutamate, some are inhibited, to initiate the signal that eventually travels through the rest of the retina and to the brain.
That is genuinely counterintuitive, but makes sense as a cascade. And that visual cycle you mentioned earlier, getting the all-trans retinal back to 11 cis in the RPE, that must take time, right?
It does. The free all-trans retinal eventually detaches from opsin, gets transported to the RPE, goes through enzymatic conversion back to 11 cis retinal, and gets transported back to the photoreceptor to recombine with opsin. This whole process is relatively slow, and it's a major factor in our slow adaptation to darkness after being exposed to bright light, which breaches a large amount of rhodopsin.
Yeah.
#TAG8, specialized retinal areas and disease.
Okay, so the entire retina isn't created equal in terms of sensitivity or acuity. We have that specialized zone for sharpest vision, the fovea centralis.
Yes, the fovea. It's a small depression, about 1.5 millimeters in diameter, located in the center of the macula lutea, and it's positioned directly opposite the pupil, in the visual axis. This is the spot for maximal visual acuity.
And why is acuity highest there? What's special structurally?
Several things. First, the overlying neural layers, the INL, IPL, GCL, and even the capillaries are actually swept aside, displaced peripherally. This creates a pit, allowing light to strike the photoreceptors almost directly, with minimal scatter or absorption by intervening tissue.
Ah, clears the path for light.
Exactly. Second, the fovea contains only cones, no rods. And these foveal cones are very long, narrow, and incredibly densely packed, maximizing the resolution.
Only cones in the fovea. Got it. And the fovea sits within the macula lutea. What's that?
The macula lutea, or just macula, is a slightly larger area, maybe 2 millimeters in diameter, surrounding the fovea. It appears yellowish, hence lutea for yellow.
Why yellow?
That yellowish hue is due to the presence of carotenoid pigments, specifically lutein and zeaxanthin, which are concentrated in the axon terminals of the photoreceptors in Henle's fiber layer and inner retinal layers here. These pigments are thought to act as a filter, absorbing potentially damaging short-wavelength blue light, and also function as antioxidants, protecting the critical central cones from oxidative stress.
So macula protects the fovea, and conversely, we have the optic disc, the blind spot.
Right. That's the area where all the axons from the ganglion cells converge, bundle together to form the optic nerve and exit the eyeball. Blood vessels also enter and leave the eye here. Because it's just nerve fibers and blood vessels exiting, there are no photoreceptors, no rods or cones at the optic disc. So any light falling on this spot cannot be detected.
The blind spot. Okay. Now, you also mentioned some non-visual photoreceptors earlier. They don't contribute to the images we consciously see.
That's a fascinating and relatively recent discovery. A small subset of ganglion cells, maybe 1–3%, contain their own photopigment called melanopsin, which also uses 11-cis-retinol. These are called intrinsically photosensitive retinal ganglion cells, iPRGCs.
And what do they detect?
They aren't great at forming images, but they're very sensitive to the overall level of ambient light intensity, especially blue light, changing over the 24-hour day-night cycle. They send their signals primarily via the retinohypothalamic tract directly to the suprachiasmatic nucleus, SCN, in the hypothalamus.
The brain's master clock.
Exactly. The SCN is the primary driver for entraining our circadian rhythms, sleep-wake cycles, hormone release, body temperature, to the environmental light-dark cycle. These iPRGCs are crucial for that synchronization.
Amazing. Okay, on the disease front, a major issue affecting that central vision area is age-related macular degeneration, AMD. This really illustrates what happens when the support structure fails at the high acuity zone.
AMD is the leading cause of irreversible blindness in the elderly and developed countries. It specifically involves degenerative changes in and around the macula. Key features often include the thickening and accumulation of drusen debris within Bruce's membrane, dysfunction or death of the RPE cells,
which disrupts support for the photoreceptors.
Precisely. This leads to the gradual atrophy or loss of the overlying photoreceptor cells, especially the cones in the macula. In the wet form of AMD, abnormal blood vessels can grow from the choroid up through Bruch's membrane, leaking fluid and blood and causing more rapid and severe vision loss. Either way, the result is typically the loss of central vision, creating blind spots or distortions right in the middle of the visual field, making reading and recognizing faces very difficult. #9. Accessory structures.
Right. Before we leave the eye completely, let's quickly touch on the accessory structures, the things that protect and maintain the optical surface, starting with that transparent membrane, the conjunctiva.
The conjunctiva is a thin, transparent mucous membrane. It covers the anterior part of the sclera, that's the bulbar conjunctiva, and then folds back to line the inner surface of the eyelids, the palpebral conjunctiva.
And it's more than just a covering.
Oh yes, it's a stratified columnar epithelium, and it's rich in goblet cells. These goblet cells secrete mucins, which are an essential component of the tear film, helping it spread evenly and stick to the corneal surface. Inflammation of this highly exposed membrane is, of course, very common conjunctivitis or pink eye.
Okay. And the eyelids themselves, they're more than just skin folds, right? They're quite complex protective systems.
Very complex. Externally, you have skin, internally the conjunctiva. In between, you have striated muscle, the orbicularis oculi, which closes the eyelid tightly, and the levator palpebrae superioris, which raises the upper eyelid. And crucially, giving the eyelid its structure and stiffness is a dense plate of fibroelastic connective tissue called the tarsus, or tarsal plate.
And embedded within that tarsus
are the tarsal glands, also known as meibomian glands. These are very large, modified sebaceous glands arranged vertically within the tarsal plate. They secrete an oily substance, meibum.
What does the oil do?
This oily secretion forms the outermost layer of the tear film. It spreads over the aqueous layer and is critical for reducing the rate of tear evaporation, keeping the eye surface moist between blinks. Blockage of these glands is common and causes achelation.
Got it. And finally, the tear producers themselves, the lacrimal glands, constantly making tears.
Yes, the main lacrimal gland sits in the upper outer corner of the orbit. It's a serous gland, producing the bulk of the aqueous component of the tear fluid continuously. Tears aren't just salt water. They're a complex solution containing water, electrolytes, glucose, urea, proteins, and importantly, antibacterial agents like lysozyme and lactoferrin.
So tears clean and protect.
They lubricate, provide oxygen and metabolites to the avascular cornea, wash away debris, and offer significant antimicrobial protection. The tear fluid flows across the eye surface, collects medially in the lacrimal lake, drains through tiny openings called puncta into the lacrimal canaliculi, then into the lacrimal sac, and finally down the nasolacrimal duct into the nasal cavity. That's why crying makes your nose run.
Okay, wow. That was an absolutely exhaustive deep dive into the eye's architecture. Incredible detail. Now let's pivot and tackle the other major sensory gateway, the ear. The vestibulo-auditory system, handling both hearing and our sense of dynamic equilibrium balance. The challenge here feels vastly different. We're converting air pressure waves into bone vibration, and finally, into the movement of fluid.
It's a completely different physical challenge, yes. And the ear's functional division mirrors that complexity. You have the external ear, which basically collects sound waves, then the middle ear, which transmits and crucially amplifies that mechanical vibration. And finally, the internal ear, very deep in the temporal bone, where that fluid movement is transduced into nerve impulses the brain can understand. Hashtag #TenacusMiedos.
All right, the external ear seems pretty straightforward. You've got the auricle, or pin of the cartilage funnel on the outside directing sound into the ear canal, the external acoustic meatus. But there's a protective mechanism here too, isn't there? Cerumen.
Yes, cerumen, or earwax. It's produced by specialized modified apocrine sweat glands, called ceruminous glands, which are located in the skin lining the outer part of the ear canal. Their secretions mix with sebum from sebaceous glands and sloughed skin cells.
Maybe it's protective?
It is. It's waxy, somewhat sticky. It helps trap dust and small particles, preventing them from reaching the eardrum. It also has some lubricating and antimicrobial properties. Sound waves travel down the meatus and strike the tympanic membrane, the eardrum.
What's the eardrum made of?
It's a thin, semi-transparent membrane. Structurally, it's composed of a core of fibroelastic connective tissue, mostly radially and circularly arranged collagen fibers. It's covered by thin skin, epidermis, on the external surface, and by a simple cuboidal mucous membrane epithelium on the internal middle ear surface. Its vibration transfers the sound energy inward.
Okay, so vibrations hit the eardrum. Then we enter the middle ear, or tympanic cavity. This is where the mechanical transmission and amplification happen, you said.
Exactly. The middle ear is a small, air-filled, mucous membrane-lined space within the temporal bone. Its main contents are the three tiny auditory ossicles. These are the smallest bones in the human body.
The malleus, incus, and stapes. Hammer, anvil, stirrup.
That's them. They form a chain connecting the tympanic membrane to the inner ear. The malleus, hammer, is attached to the inner surface of the tympanic membrane. It articulates with the incus, anvil, which in turn articulates with the stapes, stirrup. The footplate of the stapes fits perfectly into a small opening leading to the inner ear, called the oval window.
And they don't just transmit the vibration, they amplify it. Why?
They have to,
Yep.
because the inner ear is filled with fluid, which is much harder to move than air. There's an impedance mismatch. The ossicles overcome this in two ways. First, the surface area of the tympanic membrane is much larger, maybe 17 times larger than the area of the stapes footplate in the oval window. Focusing the force onto a smaller area increases the pressure.
Okay, pressure amplification.
Second, the ossicles themselves act as a lever system, providing a small amount of mechanical advantage, further increasing the force. Together, these effects significantly amplify the pressure variations, compensating for that energy loss when sound moves from air to the inner ear fluid.
Clever mechanics. Now, the middle ear is air-filled. How does it maintain pressure balance with the outside world?
Through the auditory tube, also known as the eustachian tube or pharyngotympanic tube. This is a channel that connects the middle ear cavity anteriorly to the nasopharynx, the upper part of the throat.
Okay.
Normally, the tube is collapsed, but during actions like swallowing, yawning, or chewing, muscles in the pharynx pull it open briefly. This allows air to enter or leave the middle ear, equalizing the pressure inside with the atmospheric pressure outside. That's the popping sensation you feel when changing altitude quickly, like on an airplane or driving up a mountain.
Right. And structurally, this tube can sometimes be a problem, especially in kids.
Yes, unfortunately. It's the route by which infections can spread from the nose or throat into the middle ear, causing otitis media or middle ear infection. This is particularly common in young children because their auditory tubes are shorter, wider, and more horizontally oriented than in adults, making it easier for pathogens to travel up the tube.
That makes sense. Now, are there also protective muscles within the middle ear? I think I remember reading about that.
There are two tiny striated muscles. The tensor tympani muscle attaches to the malleus. When it contracts, innervated by the trigeminal nerve, it pulls the malleus inward, tensing the tympanic membrane. The stapes muscle attaches to the stapes. When it contracts, innervated by the facial nerve. It pulls the stapes slightly away from the oval window.
What's the purpose of tensing the eardrum and pulling back the stapes?
It's a protective reflex called the acoustic reflex. These muscles contract reflexively in response to very loud sounds, usually above 80 decibels. By stiffening the acicular chain and slightly reducing the vibration transmission, they help protect the delicate structures of the internal ear from potential damage caused by excessive noise. It's not instantaneous, though, so it doesn't protect well against sudden, sharp sounds like a gunshot.
Okay, we've amplified the signal. Now we enter the internal ear. This is where the real magic of transduction happens, turning mechanical vibrations into neural signals. It's housed deep within the pitris part of the temporal bone, right? And you mentioned these nested labyrinth systems.
That's the key architectural feature. We have the bony labyrinth, which is a series of complex interconnected spaces carved out within the temporal bone. These spaces include the central vestibule, the three arching semicircular canals posteriorly, and the snail-shaped cochlea anteriorly. This bony labyrinth is filled with a fluid called perilymph.
Okay, bony labyrinth filled with perilymph.
Right.
And suspended within that.
Suspended within the perilymph, and generally conforming to the shape of the bony labyrinth, is the membranous labyrinth. This is a continuous set of delicate, interconnected, fluid-filled sacs and ducts. It includes the utricle and saccule within the vestibule, the three semicircular ducts within the bony canals, and the cochlear duct, or scala media, within the cochlea.
And the membranous labyrinth contains a different fluid.
Critically different. The membranous labyrinth is filled with endolymph.
And the ionic difference between perilymph and endolymph, you said this is the absolute key to how the inner ear works.
It is the absolute core of the ear's energy system. It's what powers the sensory hair cells. Perilymph, which fills the bony labyrinth and surrounds the membranous labyrinth, has an ionic composition very similar to cerebrospinal fluid, CSF, or typical extracellular fluid. It's high in sodium, Na+, and low in potassium, K+.
Okay, perilymph equals high Na plus Me, low K plus A, like outside a typical cell.
Exactly. Endolymph, however, the fluid filling the inside of the membranous labyrinth, bathing the apical surfaces of the sensory cells, is radically different. Its composition is unique in the body, very similar to intracellular fluid. It's extremely high in potassium, K+, around 150 millimolar, and very low in sodium, Net+, maybe only 16 millimolar.
Wow, high K plus A, low Na plus A, the opposite of perilymph. It's like an internal battery. Where is this high K plus potential generated and maintained?
The generation and maintenance of this critical ionic gradient and the associated positive electrical potential, about plus 80 milliV of the endolymph relative to perilymph, is primarily performed by a specialized tissue found along the outer wall of the cochlear duct. It's called the stria vascularis.
Stria vascularis.
It's a unique, vascularized stratified epithelium containing specialized marginal cells that actively transport K+ ions from the underlying capillaries into the endolymph. This pumping action establishes and maintains that massive electrochemical gradient across the apical membrane of the hair cells. This gradient provides the driving force for the electrical currents that underlie both hearing and balance sensation. Hashtag 12. Vestibular system equilibrium.
All right, let's tackle the two functions of the inner ear separately, starting with equilibrium. The vestibular system. You mentioned it uses two types of sensors, one for linear motion and static position, and one for rotational motion. Where are they located?
The sensors for linear acceleration, like speeding up in a car or going up in an elevator, and also for static head position relative to gravity, head tilt, are located in two sacs within the vestibule part of the membranous labyrinth, the utricle and the saccule. The sensory areas within them are called maculae. The macula of the utricle is oriented roughly horizontally, while the macula of the saccule is oriented roughly vertically.
Okay, maculae in utricle and saccule for linear motion and gravity. What about rotation?
Rotational movements of the head, like nodding yes, shaking no, or tilting side to side, are detected by sensory structures located in the three semicircular ducts. These ducts correspond to the three bony semicircular canals, oriented in three roughly orthogonal planes, superior, posterior, horizontal. At one end of each duct, there's an enlargement called the ampulla, and within each ampulla is a sensory structure called the crista ampullaris.
So crista ampullaris in the semicircular ducts detect rotation in 3 dimensions. Pitch, roll, yaw. Got it. Now, all these sensory areas, the maculae and the cristae, rely on the same basic type of sensory cell, right? The hair cells?
Yes, the hair cell is the fundamental mechanoelectrical transducer, common to both the vestibular and auditory systems. They're specialized epithelial cells.
And structurally, what defines their sensing apparatus, the part that sticks out?
The key feature is the apical hair bundle, projecting from the top surface of the hair cell into the endolymph. Each bundle consists of anywhere from 30 to maybe 100 or more stiff, unbranched, actin-rich microvilli called stereocilia. These are arranged in rows of graded height, like organ pipes, often culminating in one specialized, much longer, true cilium, with a 9+2 microtubule structure called the kinocilium. This structural polarity is critical for function.
Okay, a bundle of stereocilia and one canocilium. Now, the mechanical coupling system, how movement gets transferred to these hair bundles, differs between the maculae and the cristae, doesn't it?
It does, and that difference determines what kind of motion they detect. In the maculae of the utricle and saccule, the tips of the hair bundles are embedded in a gelatinous layer called the otolithic membrane. And crucially, this membrane contains densely packed calcium carbonate crystals called otoliths, or sometimes otoconia. Ear rocks, basically.
Otoliths. Okay, what do they do?
These otoliths make the otolithic membrane heavy and dense, much denser than the surrounding endolymph. This means the membrane is sensitive to gravity and linear acceleration. When you tilt your head or accelerate linearly, the inertia of the heavy otolithic membrane causes it to lag behind or shift relative to the underlying hair cells, bending the stereocilia.
Ah, so the weight of the otoliths translates linear motion or tilt into shearing force on the hair cells. Clever. What about the cristampulares in the semicircular ducts? How do they sense rotation?
In the cristampulares, the hair bundles project into a different kind of overlying structure, a tall, gelatinous, cone-shaped mass called the cupula. The cupula extends all the way across the lumen of the ampulla like a swinging door. Crucially, the cupula LACKS otoliths. It has about the same density as the surrounding endolymph.
So it's not sensitive to gravity or linear acceleration?
Correct. Instead, it's deflected by the movement of the endolymph fluid within the semicircular ducts. When you rotate your head in the plane of a particular duct, the inertia of the endolymph causes it to lag behind, pushing against the cupula and bending the stereocilia of the hair cells embedded within it. Each of the three ducts is optimally sensitive to rotation in its specific plane.
Okay, maculae use heavy otoliths for linear gravity. Cristae use a fluid-deflected cupula for rotation. Now for the absolutely critical mechanism, vestibular mechanoelectrical transduction. How does that physical bending of the stereocilia translate into an electrical signal using that high K plus endolymph battery?
It's a remarkably direct and fast process. The stereocilia within a bundle are linked together near their tips by fine protein filaments called tip links. These tip links are thought to be connected, directly or indirectly, to mechanically gated ion channels located near the tips of the shorter stereocilia.
Mechanically gated channels opened by pulling on the links.
Exactly. When the hair bundle is bent toward the tallest stereocilium, and the kinocilium, if present, tension is increased on the tip links. This pulling force mechanically opens the non-selective cation channels.
And because the apical surface is bathed in high K plus endolymph?
Potassium ions, K+, rush into the hair cell down their steep electrochemical gradient. This influx of positive charge causes a rapid depolarization of the hair cell membrane.
Depolarization. Okay, and that triggers.
This depolarization opens voltage-gated calcium, Ca2+ channels, located near the base of the hair cell. Calcium influx then triggers the fusion of synaptic vesicles and the release of neurotransmitter, likely glutamate, onto the afferent nerve fibers of the vestibular nerve, part of CNED that synapses with the hair cell. This increases the firing rate of the vestibular nerve.
So, bending toward the kinocilium, channels open, K plus influx, depolarization, neurotransmitter release, signal to brain. What happens if it bends the other way?
If the hair bundle is bent away from the kinocilium, the tension on the tip links decreases, allowing the mechanically gated channels to close. The influx of K+ stops, and the cell hyperpolarizes relative to its resting potential due to K+ efflux through channels at the base. This hyperpolarization reduces the baseline tonic release of neurotransmitter, decreasing the firing rate of the vestibular nerve.
Wow, so it's directionally sensitive. More firing one way, less firing the other way, compared to a baseline rate when the bundle is straight. It provides continuous proportional signaling about head movement.
Precisely. It's an incredibly sensitive analog system.
And medically, this direct mechanical linkage explains why physical misplacement of things, like those otoliths, can cause such intense symptoms. Like in BPPV, benign paroxysmal positional vertigo.
BPPV is a perfect example of this mechanical system going wrong. It's thought to occur when some of the otoliths become detached from the macula in the utricle, perhaps due to age or head trauma, and migrate into one of these semicircular canals, most commonly the posterior one.
So now you have loose rocks in the rotational sensor.
Exactly. These loose otoliths are called canaliths. When the person moves their head into certain positions, like lying down or rolling over in bed, gravity causes these dense canaliths to move freely within the endolymph of the affected semicircular duct. This movement inappropriately drags the endolymph and deflects the cupula of the crista ampullaris in that duct.
Even though the head isn't actually rotating in that plane?
Correct. This deflection sends a powerful false signal to the brain, indicating that continuous rotation is occurring. The brain's attempt to reconcile this false vestibular signal with conflicting information from the eyes, which see stationarity, results in the characteristic brief but intense spinning sensation, the vertigo, often accompanied by nystagmus, involuntary eye movement. It's a purely mechanical problem, often treatable with specific head maneuvers designed to reposition the loose otoliths back into the utricle. #tag 13. Auditory system.
Okay, fascinating. That covers balance. Now, let's shift to the auditory part of the inner ear, housed in that coiled snail shell structure, the cochlea. We need to understand the cochlear duct, or scala media. This is where the sound wave energy transmitted through the middle ear is finally transduced into neural signals for hearing.
Right. The cochlear duct, scala media, is the triangular endolymph-filled tube that spirals up the center of the cochlea. It forms the middle compartment. It's separated from the perilymph-filled compartment above it, the scala vestibuli, by the very thin vestibular membrane, also called Reisner's membrane.
Okay, scala vestibuli above, filled with perilymph.
And it's separated from the perilymph-filled compartment below it, the scala tympani, by the much thicker and structurally complex basilar membrane.
Basilar membrane below, also perilymph in the scala tympani. Do the top and bottom scalae connect?
Yes, the scala vestibuli, which starts at the oval window,
Yeah.
and the scala tympani, which ends at the round window, another membrane-covered opening back to the middle ear, are continuous. They communicate only at the very apex, the tip of the cochlear spiral, through a small opening called the helicotrema.
Helicotrema at the apex. Got it. Now, the actual sensory apparatus for hearing, it sits on the basilar membrane within the cochlear duct, right? The organ of Corti?
Yes, the organ of Corti, or spiral organ, rests directly on the basilar membrane. It's an extraordinarily complex and delicate strip of sensory and supporting cells that runs the entire length of the cochlear duct. This is where auditory transduction happens.
What are the key cell types in the organ of Corti? We still have hair cells.
We do, but they're specialized for hearing. There are two main types, and interestingly, unlike vestibular hair cells, auditory hair cells typically lose their kinocilium during late development, leaving only the stereocilia bundle. First, there are the inner hair cells, IHCs. They form a single row along the entire length of the cochlea, totaling about 3,500 cells. They have a flask shape and a fairly linear or slightly curved array of stereocilia on top. Critically, the IHCs receive the vast majority, about 95%, of the afferent nerve endings from the auditory nerve. They are the primary sensory receptors for hearing.
Okay, IHCs, example single row, primary sensors. What's the other type?
The outer hair cells, OHCs. These are much more numerous, arranged in 3 to 5 rows, totaling about 12,000 cells. They are typically more cylindrical or columnar in shape, and their stereocilia are arranged in a distinct V or W shape. They receive far fewer afferent nerve endings, but extensive efferent innervation from the brain. Their role is different.
Different role. We'll come back to that. What else is in the organ of Corti? Is it just hair cells?
No, there are several types of specialized supporting cells that provide structural and metabolic support. These include the inner and outer phalangeal cells, which surround and support the base of the hair cells and send processes up to form the reticular lamina, a tight apical plate. There are also inner and outer pillar cells, which are tall, stiffened cells containing microtubules and keratin that outline a central triangular space called the inner tunnel. This tunnel runs the length of the cochlea and likely plays a role in maintaining the structural integrity and perhaps the unique ionic environment around the hair cells.
Okay, supporting cells forming a scaffold. And the whole organ of Corti is overlaid by something, right? The tectorial membrane.
Yes, this is a cellular, gel-like ribbon or flap that lies over the organ of Corti. It's secreted by cells in the nearby spiral limbus and consists mainly of collagens, glycoproteins, and proteoglycans. It extends out over the hair cells.
And how does it interact with the hair cells?
This is key. The tips of the tallest stereocilia of the outer hair cells are physically embedded in the underside of the tectorial membrane. The stereocilia of the inner hair cells, however, are generally thought to be freestanding, likely deflected by the movement of endolymph fluid in the narrow space just beneath the tectorial membrane.
Okay, OHCs embedded, IHCs free. Now let's trace the pathway. Sound waves vibrate the eardrum, amplified by ossicles, push the stapes footplate into the oval window, What happens next in the fluid?
That movement of the stapes footplate creates pressure waves in the perilymph of the scala vestibuli. Because liquids are incompressible, this pressure wave travels up the scala vestibuli.
Does it go all the way to the helicotrema?
Some low-frequency energy might, but the crucial thing is that the pressure wave exerts force downwards, causing displacement of the structures separating the scala vestibuli from the scala tympani primarily, the basilar membrane.
Ah, the pressure wave makes the basilar membrane move up and down.
Exactly. The pressure wave effectively bulges the basilar membrane and the overlying organ of Corti down into the scala tympani, and the pressure is then relieved by the bulging outward of the round window membrane back into the middle ear space. So you get a traveling wave of displacement along the basilar membrane.
And here's where the frequency mapping, the tonotopy, comes in. How does the cochlea sort frequencies?
This is the genius mechanical design. The basilar membrane is not uniform along its length. It's structurally heterogeneous. Near the oval window at the base of the cochlea, the basilar membrane is relatively narrow and stiff. As you move toward the apex, near the helicotrema, it becomes progressively wider and much more flexible or compliant.
Different stiffness along its length.
Precisely. This gradient in mechanical properties means that different frequencies of sound cause maximal displacement at different locations along the basilar membrane. High-frequency sounds have enough energy to displace the stiff basal region, but dissipate quickly. They cause maximum vibration near the base.
High-frequency base.
Low-frequency sounds travel much farther along the membrane before finding the region flexible enough to displace maximally. They cause maximum vibration near the wider, more flexible apex. Intermediate frequencies peak at intermediate positions. The cochlea essentially performs a mechanical Fourier analysis, spreading out the sound frequencies spatially along the length of the basilar membrane.
So the location of maximum vibration tells the brain the pitch. Incredible. Now, when the basilar membrane moves up and down at a specific location, how does that activate the hair cells sitting on it?
As the basilar membrane moves up, the organ of Corti moves with it. Because the tectorial membrane is hinged differently at the spiral limbus, and the outer hair cells stereocilia are embedded in it, this creates a shearing motion between the tectorial membrane and the reticular lamina, the apical surface of the organ of Corti. This shearing force bends the stereocilia bundles.
Bending the stereocilia. And that opens the channels, just like in the vestibular system.
Yes. Bending the stereocilia towards the tallest row increases tension on the tip links, opens the mechanically gated K+ channels, allowing K+ influx from the high K+ endolymph, causing depolarization. Bending away closes the channels, causing hyperpolarization.
Okay, so that explains how the inner hair cells, the primary sensors, get stimulated and release neurotransmitter to signal sound. But what about the outer hair cells? You said their role was different, and you mentioned amplification.
Yes. This is the truly jaw-dropping part. Cochlear amplification, powered by the outer hair cells. They aren't just passive detectors waiting to be sheared. They're tiny biological motors.
Motors! How?
When the mechanical deflection of sound causes the OHC stereocilia to bend and the cell depolarizes due to K+ influx, something remarkable happens within the OHC itself. These tall columnar cells undergo an incredibly rapid change in length. They shorten upon depolarization and lengthen upon hyperpolarization.
They physically contract and elongate with the sound wave.
Yes, at acoustic frequencies. This rapid voltage-dependent motility is mediated by a unique motor protein densely packed in the OHC's lateral cell membrane, called prestin. It acts like a piezoelectric element, changing shape in response to changes in membrane potential.
Okay, they shorten when depolarized. What does that achieve?
This rapid shortening acts like a tiny piston. Because the OHCs are embedded in both the basilar membrane below and the tectorial membrane above, via their stereocilia, their contraction actively pulls these two structures closer together or pushes them apart in phase with the sound vibration.
They're actively pumping the system.
They are literally adding mechanical energy back into the system. This electromotility of the OHCs physically amplifies the vibration of the basilar membrane, particularly for low-intensity sounds. It also sharpens the tuning, making the peak of the traveling wave narrower and more defined.
So they boost the signal before the inner hair cells detect it.
Precisely. They act as a cochlear amplifier. Their motor action enhances the mechanical stimulus to the fluid movement or shearing force that reaches the stereocilia of the nearby inner hair cells. This allows the IHCs to respond much more sensitively and selectively to faint sounds. The OHCs refine and amplify the input before the IHCs, the main sensors, send the final high-fidelity signal about frequency, intensity, and timing to the brain via the spiral ganglion neurons, CN8.
That is absolutely incredible. The outer cells are essentially feedback motors, amplifying the input for the inner sensors. Understanding this distinction must be key for understanding hearing loss and treatments like cochlear implants.
Absolutely. For instance, damage to OHCs, which are quite vulnerable to noise exposure, certain drugs, and aging, is a very common cause of sensorineural deafness. This often results in not just a loss of sensitivity, difficulty hearing quiet sounds, but also poor frequency discrimination, difficulty understanding speech in noisy backgrounds, because the sharpening effect of the cochlear amplifier is lost.
And cochlear implants, how do they work, given this complexity?
Cochlear implants are designed for profound sensorineural hearing loss, where the hair cells themselves, both inner and outer, are largely non-functional, but the auditory nerve fibers are still intact. The implant bypasses the entire damaged mechanical transduction system, the middle ear, and the hair cells. It consists of an external microphone and processor and an internal implanted part. The internal part includes a receiver stimulator and, crucially, a thin array of electrodes that is surgically threaded into the skull at tympani, lying close to the wall where the auditory nerve fibers run.
Directly stimulating the nerve.
Yes. The external processor analyzes the incoming sound, breaks it down into different frequency components, and sends signals to the internal device. The internal device then delivers tiny electrical pulses via specific electrodes along the array. Because of the cochlea's tonotopic organization, stimulating electrodes near the base produces a perception of high pitch, while stimulating near the apex produces a low pitch. The implant directly stimulates the nerve branches corresponding to various frequencies, providing the brain with the necessary patterns of neural impulses to interpret sound, including speech. It's a remarkable feat of bioengineering, leveraging that fundamental tonotopic map. #outro.
Wow. We have truly gone deep today. We have, I hope, achieved a level of mastery over two immensely complex yet elegant sensory systems. We've mapped the absolute architectural necessity of things like orthogonal type I collagen in the avascular cornea. We followed the precise flow of low-protein aqueous humor and the consequences when it fails. We've defined the critical structural differences between those constantly shedding rod discs and the continuous cone invaginations, and understood the counterintuitive cascade of phototransduction.
And then in the ear, we've synthesized the intricate structure of the bony and membranous labyrinths, really understood the critical importance of that high K plus endolymph gradient maintained by the striga vascularis.
The internal battery.
The internal battery, exactly. And recognized the sophisticated dual function of hair cells, especially in the cochlea, acting both as primary sensors, like the inner hair cells, and as these incredible dynamic mechanical amplifiers, the outer hair cells. It really underscores how both systems rely utterly on precise structural geometry and highly specialized cells to convert environmental input, light or vibration, into neural signals.
So, building on all that detail, here's a final provocative thought for you, our listeners, to carry forward. Something that ties these two incredibly sophisticated sensory gateways together, yet highlights a fundamental difference. We observe this deep symmetry in using specialized cells and ion flows, yet there's a radical reversal in the polarity of the initial signal.
Think about it. In the eye, the detection of the stimulus light causes the primary photoreceptor cell to hyperpolarize. It becomes more negative. And the signal to the brain is initiated by a reduction in its baseline neurotransmitter release.
Right. Light turns the signal down initially.
But in the ear, the detection of the stimulant, the mechanical bending of scariocilia towards the tall edge, causes the primary hair cell to depolarize.
Yeah.
It becomes less negative. And the signal is initiated by an increase in neurotransmitter release above baseline.
So sight starts with hyperpolarization and less transmitter. Hearing starts with depolarization and more transmitters.
Why? Why does evolution dictate that our primary sensory gateway for sight initiates its crucial signal by turning off or reducing the baseline input, while our primary gateway for hearing and balance initiates its signal by turning on or increasing the output?
What does this fundamental reversal in polarity tell us? Maybe about the evolutionary constraints, the energy requirements, the baseline noise levels, or perhaps the signal processing strategies of these two highly sophisticated, constantly active sensory systems.
Ponder that difference. Consider the implications of starting from on versus starting from off as you navigate the sensory world today.
We'll see you next time for the next deep dive.